not much to record. I'm going to put up the screen. I don't have much to put up here, but I will put up the whiteboard. I'll try to put up the whiteboard. Okay. Um, and if push comes to shove, I'll try to draw a picture or something on the whiteboard. Now, for some reason, when I do that, I lose my picture in the corner. I now have got Dawson's black screen here with his name on it. And so I can't see if when I hold up the sheet to the camera, if I've got it centered or not, or you can read it. So let me know, move it right, left, front, back, tell me what to do with it. Before Dawson came in, I had him there, but I had my picture, but I don't anymore. So anyway, let's get going. Any questions from last time or this time? Right. Well, I, I, like I said, I can see one block. Like right now, it's yours, Melissa Hall. I see yours, your name, not your camera. I guess y'all turn your cameras off, so I just see the name. I've got plenty of whiteboard on here, but what the problem is, one of the problems is if I have the participants up, it's right in the middle of my whiteboard. And I don't know if this is able to, yeah, I guess I can move that around, but it still will just about always be in the right. You can't see that, I don't think, can you? The participants, a big block. Oh, you don't have the list of the people. Oh, okay, right. In that box. And you see me move the box around? Oh, you don't. Where is it? In the middle of the screen then? Okay. Yeah, mine is right in the middle of the screen, but I can move it, but it's still a big box that's in the way. So if you see someone else try to get into the class, let me know because I'm going to minimize now mine. So, well, right now it's not going to matter, but if I start writing, I'm going to minimize it so that I can write on the screen. Um, so now I guess I'll leave it open. I think I'll move it over to this side and that way I'll see if anyone else tries to come in. All right, good deal. I take it you've done Zoom before? Uh, well, I'll be asking you for help then. My wife will thank me because I'm always asking her for help. Okay. So, Ricky, we left off last time. Ricky, do you have a book or an ebook or something like that? Second, you don't? Okay, well, I'll try to put as much down as I can. Um, the I can't remember if we did it last summer or not, but also on the syllabus, there is under content, there is a thing called the web assign class key or something like that. Math 238 web assign class key. I can't remember exactly how I entitled it, but titled it, I think is a better word. But there you'll find the key. If you are on the Cengage, whatever they call it, unlimited, uh, all you have to do is enter that code and you get a copy of the ebook. I think that's what you use, isn't it, Dawson? Oh, his microphone's off. Uh, okay. Melissa, you got a physical book or are you using the ebook? Oh, you have a copy of the ebook. Right. Okay. Now, when you say a copy of it, did you get it through Cengage Unlimited, or did you get it some other way? You were what? I see. Okay. Uh, well, can someone send it to Ricky? Is that something that can be done? Okay. So try that, and then you'll all have a copy of the ebook, and that'll be due. I don't have a copy of it. I have a physical copy. Maybe I could get it, but it's just another thing. I'm a dinosaur, and these things are confusing enough to me. So if y'all can manage to do that, that may be helpful for everyone then. All right, so we're on, and I know that in the ebook they don't do by page numbers, but we're in chapter 1, which is Introduction to Differential Equations, and section 1.1 is definitions and terminology. And that's basically what we're doing now is just getting terminology down. Some of this is useful and you'll run into it again. Others of it are terms that they say, this is what we generally call it, and then I don't ever recall them calling it that again. Okay, but for instance, the last thing we did, and it's where we start today in example 3, on page 5, as you can tell where page 5 is, but example 3, the normal form of an ordinary differential equation. Okay, now that was the last definition we had. And here were the two things they had in the text. I don't know, is this one right here, the dy dx equals some function of x and y? Do you see that on the in my block? Okay, that would be the normal form for a first order differential equation. You just separate the dy dx, and in everything that doesn't have a derivative in it, all your other x's and y's are on the other side. Now that will be a little later in this section, or the next section coming up real soon. That will be a very useful form to have. And that I can see why they call it a normal form. This would be the normal form for a second order differential equation. Can you see this one? Have I got it on the screen well? You pull out the highest derivative, dy d2y dx squared, second derivative of y with respect to x, and then put everything else on the right-hand side. Well, this everything else on the right-hand side has a bunch of x's in it, could be a bunch of y's, and also any of your y primes you would have. This, to me, I cannot think of a situation where that would be a useful form. So why do they say the first order? Yes, we'll see where that comes in to be very, very useful. For second order and higher, I don't see any purpose in specifying a normal form. Oh, we've got Cole waiting. Oh, should we let him in? What you think? Okay. Okay, he still doesn't have a microphone on yet, but let's get him here. Okay. Ricky, Ricky, did you hear that? Okay. All right, Cole, you in here? All right, good deal. I saw that you saw or I figured it was you who saw the message last time. Now, were you and Corbin both there last time? Right. Okay. Did y'all have a good time? Okay. Um, all right, but was it reasonable to get into this one? Okay. All righty. Yeah, I think it was Billy told me last time that, or maybe it was Melissa, that one of them saw y'all in there, and we tried to send you messages and other things to come to the Zoom. And I thought, in fact, I think I probably did mark you present just because you were trying to be there. So, um, but here's the deal, and you were in my class last summer, right? Okay. Um, I'm running Screencast-O-Matic like we did last summer, right? So you can go to YouTube video under this class, and the link is on Blackboard in the content. There's the syllabus. There's, I can't remember the order, the research paper, general instructions, um, my locator card, the uh, the code, the class key for WebAssign. I don't make any web assignments. I make assignments, but no web assignments. And the things, and then there's a link there for the YouTube videos. There's also a few other links to either websites or YouTube videos or other things that some students have told me they found useful, or I found and thought they might be useful. They're under content as well. But you can go to the YouTube videos, click on that, and hear and see a little bit of everything we did in class last time. This book, Differential Equations, just like Dawson, the linear algebra last term, they do not have PowerPoints with them. So there aren't any PowerPoints for me to show. I didn't put them on the content. Uh, I do everything, or I used to do everything on the screen with my ionizing pen on the writable screen. I've got a whiteboard here, but I have to use my keypad and draw on it. And that is awful. It is terrible. It's unreadable almost. Or I can do text and type on it, and that is slow and awful as well. So, and it doesn't allow places for superscripts and subscripts. It's just really fairly useless. But I have it up here just in case there's something I need to show you. What I'm doing, I don't know if this is being recorded or not, but when I talk about something, I hold it up in front of my camera. I encourage you to have a pencil and paper and be working the examples as we work them in class. And then if anyone's having problems, I'm working them at the same time, and I'll show you what I'm getting, just like this. Now, right. Now, whether that's recorded on the YouTube video, I do not know. So we did some of these last time. So some of you, if you could go out there, especially Cole, if you wanted to go out and check everything we did, see if you can see the camera shots. I just don't know. I know it records everything that would be projected on the screen, but I never used the camera in class because I was there in class. So I don't know if the camera shot is recorded or not. Since you see it in a small window in the thing, perhaps that is being recorded, but it'll be awfully small. I know that Melissa said you can expand that and see it bigger. So if you're wanting to, I don't know. I just don't know. I don't know how this technology works. I think it's just what uh, is is being shown on the screen, uh, but not your screen. But I don't know if it's everything on my screen or not. So, for instance, I have a box down here with all of your names in it. If I don't think that's being projected, but maybe it is. So I don't know. I haven't been there to check. So, any questions before we get going again? Okay. We're just talking about we're on, do you have an ebook, physical book, or just one by the seat of your pants? Ebook, okay. I know they probably don't have page numbers in it, but we're in chapter one, introduction to differential equations, section 1.1, definitions and terminology. We're on the fifth page of that, but I think what you have to look for is example 3. That's where we're beginning today. Okay. And I was just reviewing what we did last time. What I showed you just a few minutes ago, this is one way to write a differential equation. put the highest order derivative on the left-hand side and everything else on the right-hand side. That's called the normal form for a differential equation, okay? This is a first order differential equation, meaning the maximum derivative is the first derivative. This is the second order differential equation. I don't know if I have it on the camera right or not. The maximum derivative is the second order, so you put that on the left-hand side and everything else on the right. All your x variation, your y variation, and your y prime variation. All that goes on the right-hand side. This one, for first order differential equations, that is a form we will use. We'll use in several situations. This one, I can't think of a time when it's advantageous to write it in normal form for a second order or any higher order differential equation. First order, yeah, there are places where it works, but they're asking us to do this just to make sure you understand the terminology in case later in the text they'll say, write this in normal form. You say, wait, what's normal form? Well, that's when the maximum derivative is isolated on one side, the left-hand side, and everything else is on the right-hand side. So example 3, if you've got it now, is this one. Here's the differential equation. 4x times dy dx plus y equals x. Okay, before we go any further than that, with this, let's just do a little bit of review for those who weren't here last time. What is the type of differential equation this is? Okay, first, is this a differential equation? Yes, it has a derivative and it has an equal sign. That's all it takes to be a differential equation. Okay, what order differential equation is this? First order. The maximum derivative is a first derivative right here. Okay, is this linear or nonlinear? Have we hit that yet? No, we haven't. That's coming up. Okay, we'll get to that in a minute. Okay. So how do we write this in normal form? Isolate the maximum derivative, which is your dy dx. So it's just like solving for x. Now you're solving for that maximum derivative. Subtract y from both sides. Okay. I'll do it in gory detail here. That would be 4x times dy dx. The plus y minus y goes to 0 is equal to x minus y. Okay. Still not isolated until we divide both sides by 4x. Okay. So dy dx is equal to, I'm writing with pencil, I meant to write with pen, is equal to, and yep, I write it in the same form, x minus y over 4x. Now there's a variety of ways you can write that. Now tell me something, is that pencil dark enough for you to see easily, or would it be better in ink, black ink? It is? Everybody okay with it? Okay. Because I'll make a confession here. When I do, I've got to get something just a second. When I do math, I tend to make errors. So I prefer doing pencil. And what I just remembered is I carried, when we were away this weekend, I carried my eraser with me and forgot to get it out of my bag. So there's my eraser back. Okay, that's where I was heading. So if that's visible, I'll stay with the pencil then for a while. Okay, so this is the normal form for that differential equation. Okay, and like I said, we will be using this form, and I can really think of only one instance where it's handy. And we'll be doing that this chapter. I'm pretty sure it'll be this chapter, and we'll use that. Pretty simple process. Any questions on it? That's it. That is what we want to do to get it, excuse me, in normal form. Like I said, useful in one case I can think of. Well, not really. There's others too that it might be useful to do that. But yeah, that's the goal. Now, the second part, the B part, here's your equation. Now, this is written in prime notation, not Leibniz notation. That last one was not Leibniz notation. In prime notation, y double prime minus y prime plus 6. And the book has an error here, okay? Unless you can convince me there's some way that this is not wrong, they have an error here, okay? What would be your approach to get that into normal form? Can you see it on the camera shot? Okay, what would be your approach? And the 6. Yeah, right, okay. That's exactly right. That would be adding y prime to both sides and subtracting 6 from both sides. I do it in gory details, so just so everybody can follow. The two of those go out on the left, and you're left with y double prime is equal to y prime minus 6. Now, how in the world in the book they got a 6y there? I do not know. Okay, is that on the ebook that way, or is it just minus 6? In the written text, it says y double prime equals y prime minus 6y. There was no 6y on the left, on the first side. How they got it there on the second? What does your ebook tell you? What's your answer? It has a y on there after the 6, right? Yeah. That's wrong. Or you convince me that it's not wrong, and I'll take your word for it. But I see no way they got a y in there. Either they left off the y on the first on the given problem, or they accidentally put it on the solution. But it's wrong. Whichever way, it's wrong. So the book does make errors too, and they don't always erase. Okay. So any questions about that? And like I said, I cannot think of any reason to do a second order or higher order differential equation in normal form. I just can't think of a single instance that I would ever use that. For the first order, yes. I can think of a couple of really pretty decent times and situations where you'd want to do that. But why give it a special name? I don't know, but that's what they've done. All right, so we've done classifying differential equations by type, and there's only two types. Ordinary ordinary differential equations like we've been dealing with here, or partial differential equations like we dealt with last time. I don't have that on this piece of paper. That was on the previous piece. Let me see if I can find it here. Yeah, there was an example of a partial differential equation, this one right here. We're not doing partial differential equations in this course. This course is ordinary differential equations. But they just mentioned it because that is a classification of differential equations. Now, that's not to mean that we're not doing partial derivatives. We will be doing those in at least one particular type of differential equations in order to go about solving them. And we will be taking some partial derivatives, but we're not solving partial differential equations. So the type, all we're interested in is ordinary differential equations. The degree we've just seen, that's the highest derivative taken in the problem. Okay. Now we move to linearity. Now, if you think about it, type is binary. It's either ordinary or it's partial. Order basically is almost infinite. We're not going to infinite, but we'll usually do first orders mostly. We will do, first order. We'll do quite a few second order. We'll do some third and fourth orders, and maybe a few higher, but not very many higher. Okay. So we'll usually be stuck with first or second order. Not quite binary, but we will usually deal with the lower order. Linearity is also a binary issue. A differential equation is either linear or it's not linear. Okay. Yes or no. Linear or nonlinear. Okay. So it's another binary situation. We will be doing some of these. Okay. Mostly linear, but we will do some that are not linear. Okay. Now, what does it mean to be linear? Okay. Now, if you have, all of you now have, well, maybe you don't have it yet, but you'll be getting your ebook soon. An nth order, now that could go up as high as you want that order to be, an nth order differential equation, okay? And they're referring up to this form here. If you don't have your book, I'm going to try to show. Has that got the capital F in it? Do you see that? Okay. That differential equation with n being the order, that's the form we're talking about. Some big function that can take x's and any function of x you choose to have. Any function of x you choose to have. Y's, y primes, y double primes, y triple primes, all the way up to the nth derivative of y. And for those who weren't here last time, let me point this out to you. When you're using prime notation, you only use y prime, y double prime, and y triple prime. They don't even show that here. Anything past that, we put the order of the derivative in parentheses. You can't put it as a superscript without, you would think that's y to the fourth power. No, it's the fourth derivative. So anytime you see a superscript in parentheses, that's the order of differentiation. Okay, I said fourth. That it's the nth order, whatever the maximum, or yeah, the maximum would be. Okay, now with that form, okay, is said to be linear if f is linear in all the y applications. In other words, your y's, your y primes, your y's double primes, your y triple primes, all your y's are only first order. Okay? Oh, wait, okay, first degree. Let me say it that way. Because we're using the terms more specifically now. Only first degree. Now, we'll see some examples of this, but for an equation to be linear, y is equal to mx plus b. What makes that a linear equation? Okay, I'll write it down. I'll pick an equation here. 4x y plus y equals x. Okay, that's sort of a dumb equation. Now, and it's not a good equation for this answer, for this question. I'm sorry. Okay, it's a dumb equation, I admit. 4x plus y equal x. Is that a linear equation? Yes. What makes it a linear equation? Okay, there is an exponent, you just don't see it. It's 1. Yes, right. The only power for your variable in any term is the first power. This is x to the first power, y to the first power, and x to the first power. Of course, that could be written more simply as 3x plus y is equal to 0. But it's still a linear equation. It's x's and y's both have exponents only of 1. Okay? Now let me write another. 4x plus sine y is equal to, let's just make that 7. Okay? Is that a linear equation? It's linear in x, but not linear in y, because that does not form a straight line. A sine y is a sinusoidal curve, okay? It is not linear in y. Yes, y is only to the first power, but this sine takes the y and makes it into a curvilinear situation. That is not linear in y. It is linear in x, but not in y, okay? So that's what we're talking about with a uh, uh, differential equation when we talk about it being linear. Now this is going to take quite a bit of room to write, so I think I need to find me, oh here, okay, I was on the wrong side. Here is the most convoluted way you could write this. I'll try to get it done. A sub n x d, the nth derivative of y with respect to x, plus a sub n minus 1 x times the n minus first derivative of y with respect to x to the n minus 1 plus dot dot dot. You would write more terms of this, so I have to leave enough paper for it. A sub 1 of x dy dx plus a sub 0 as a function of x times y, and this is equal to some g of x. I still didn't leave enough room. Okay. That is about the, okay. Now, let me just explain some things here. And this is very reminiscent of polynomial equations, okay? Your coefficient here, the subscript n, does nothing but tell you that this polynomial function goes with the nth derivative of y. That's all this n tells you. This n is important because that's how the order of your derivative is, okay? But this n just tells you this is the coefficient function that goes with that derivative. The a sub n minus 1 of x goes with the n minus first derivative of y with respect to x. And then you step on down until you finally get to the a sub 1 x times the first derivative of y with respect to x, and then times a sub 0 of x times y, and that's equal to, this is where I ran out of room, equals to some g of x. Now let's think about these, what I call the coefficient functions. The a functions here, they're all functions of x. The g over here, that's a function of x. Those can be any functions of x in the world, okay? They can be squares, cubes, radicals, sines, cosines, tangents, exponents, logs, all kinds of functions of x. No limit there. What makes a linear differential equation is that the derivative forms your nth derivative of y, your n minus first derivative of y, your n minus second, your n minus third, your first derivative of y, your third derivative of y, second derivative of y, first derivative of y, and y itself, they only have exponents of 1, okay? And they're not written as the argument of a nonlinear function. Like this last one, that could be sine x times y, the y being separate from the sine x, not as the argument of that, but it couldn't be x times the sine of y. That would make this nonlinear, okay? Does that make sense? So each of these only shows up in every term as a derivative, the derivative to the first power, okay? Whatever order the derivative is not. Notice what you don't have. You don't have a term with a the third derivative of, the third derivative of y times the first derivative of y. No, that's not allowed. That's not linear. Just like the one that I had here when wherever it was, when I had x times y, I decided to take that out because that wasn't linear, because x times y is not a linear function. For x, that's linear. Y, that's linear, but for xy would not be linear because now you have two variables. Now you can have x times a derivative of y, that's no problem, but you can't have a y times a derivative of y. That would not be linear, okay? So I probably made this just about as confusing as I can, but that's all it means to be linear, okay? Now, they mention here two special cases of this, and the reason these are special, we are going to be solving these by special methods, okay? So here's the first of these. If you just have a first order differential equation that's linear, it would be a sub 1 of x times dy dx plus a sub 0 of x times y is equal to some g of x. Okay? That's a first order, ordinary, not partial, differential equation that's linear. The dy dx is the only place you see a y in that term to the first power. The y here, only place you see a y here, no other derivatives of y here, and that's to the first power, and all your coefficients and the thing to the right are all functions of x. Any function of x. You know, they don't have to be linear. It's only the y's and the derivatives of y's have to be linear. That's a first order linear differential equation. Second order differential equation, very similar to that. A sub 2 x times the second derivative of y, 2y dx squared plus a sub 1 of x dy dx plus a sub 0 of x y is equal to some g of x. A second order ordinary linear differential equation in the derivatives are derivatives of y, the d2y dx, first power, dy dx, first power, y, first power, no cross terms in it, and all your other coefficients can be any function of x that you want, including the thing on the right-hand side. A second order linear differential equation in usually say in x, the independent variable, but differential equations with respect to y. I mean, derivatives of y. Okay. Now, I've been harping at this, and here's how they say it. In the additive combination of the left-hand side of that big equation I wrote, okay, equation 6 that you see on your, or will see on your ebooks when you get them, we see the characteristic two properties of a linear ordinary differential equation. The dependent variable y and all its derivatives, y prime, y double prime, up to y, the nth derivative of y, are all of first degree. That is, the power of each term involving y is 1. That's what I've been saying. Here's how the book says it for those who don't have the book yet. Okay? The first point. All the powers of your y's and your derivatives of y's are 1. Okay? And secondly, the coefficients A0, A1, A sub n, of those y's, y primes, y double prime, and y, the nth derivative of y, depend at most on an independent variable of x. You can't bury a y in those coefficient functions. It's only functions of x. Now, the part they didn't say, and they sort of imply it in the first part, you can't cross any of the terms. In other words, you can't have a term in it with a second derivative of y and a y. You can't do that. You can't have any more than one form of y in any term, and that has to be to the first power. Okay. A nonlinear ordinary differential equation is simply one that's not linear, okay? Pretty clear. Binary here, okay? Nonlinear functions of the dependent variable or its derivatives, such as sine y, e to the y, they can't be anywhere in the problem. Once they show up somewhere in any term, right hand, left hand, any term, if you have a y in anything other than just y, or a derivative of y in any other function that's not a linear function, it's not a linear equation. So here are going to be a couple of these, okay, for you to evaluate, okay? Here we have, and this is written in a sort of a strange form, one that we saw last time, y minus x dx, this is in differential form, plus 4x dy is equal to 0. Now, just looking at that, this one right down here, okay, is that on the screen? This one? Y minus x dy, okay, it's there, okay. That one, maybe not too obvious of whether that is a linear or not. Here's how you tell. Multiply through. Y times a dx, that's not going to bother anything. That's linear. X times a dx, no problem. That's only x's. Here you have 4x dy, no problem there either, because you only have a dy in this term. Now, what you could do here, this would drive some pure mathematicians crazy, divide everything on both sides by dx, and it becomes more obvious. So let's do that. Okay. That's not really what you're doing, but it's writing it, changing from differential form to derivative form. That's basically it. That'd be y minus x plus 4x dy dx is equal to 0. Now that's a bit more obvious, okay? If you rewrite it that way, in other words, basically dividing everything by the dx, getting your derivative here all together, now you have y minus x plus 4x dy dx equals 0. If you wanted to write it in sort more standard form or normal form, whichever you'd want to call it, 4x dy dx plus y is equal to x. Yeah, that's linear. The only place a y shows up here is in the first derivative. Only place the y shows up here is by itself. The x can be anywhere in any power. This happens to be linear in x as well. Okay, but that doesn't matter. Those are the coefficients. Did that make sense? I know my paper, I don't hold it very steadily. Okay. Say this again. Okay. You're fading out awfully badly. Oh, what would make it nonlinear? Okay. This one was linear. Okay. Yeah, I'm sorry. Yeah, this one is linear, wherever it was. Right down here, my hand's covering it. Yeah, this is linear because here the y is only times the dx. This would have x dx. That doesn't really matter. This would be 4x dy dx. See, there's no single term with a y and a y prime, or y to any other power, or y prime to any other power. When you rewrite it like this, it's a little more obvious. This y is by itself, the x, who cares? And this is 4x, that's only a function of x, and that's only a derivative of y. So that is linear. Yeah. Right. Yeah. Yeah. You could rewrite this as 4x dy dx, put that in the front, plus y, and then move the x over here equal x. That would look just like some of the forms we did earlier. Linear in a linear function of y. Okay. The second one I think is even easier because it's in prime notation. Y double prime minus 2y plus y equals 0. Is that linear or nonlinear? This one right here. Y double prime minus 2y plus y equals 0. I think it's how it is, yeah. Okay, what makes it nonlinear? Except that you can add those two together and make it minus y equals 0. Yeah, that's still linear. I don't know why they wrote it this way, but they did. Just rewrite that y double prime minus y equals 0, and that indeed is linear. Now, what if it had been that as our original problem? Y double prime minus 2y squared plus y equals 0. That's nonlinear because a y or its derivative is raised to a power other than 1. Right? That would be nonlinear. This one's linear. That one's nonlinear. Okay? Does that make sense? Okay. Now, what if that would have been y to the 2 power? That's not a square, but it's still not a 1. Okay? That exponent cannot be anything but 1. It can't be a 1/2. It can't be anything but a 1.001. That would not be linear. Okay. Now, let's look at the third one here. It's a little more convoluted looking, but let's see if we can figure it out. X cubed d3y dx cubed plus x dy dx minus 5y is equal to e to the x. Okay, first, what type of differential equation is this? I got to find it here. This one right here. What type is it? Ordinary. What degree, what order is it? Third order, perfect. Okay. Linear or nonlinear? Why is it nonlinear? X can be to any power in the world. That could be e to the x. It could be a log x. Doesn't matter about the x's. All that matters are the y's and derivatives of y. This is the third derivative of y, but it's only to the first power. This is the first derivative of y. It's only to the first power. This is a y, even though it's a 5y, it's only to the first power of y. And whatever you had over here, e to the x, that doesn't matter. The x can be any functions in the world. It's only the y's and the derivatives of y's. And they can't be multiplied by each other either. Like you couldn't have a y triple prime times a y prime. Couldn't have that. So this happens to be linear. It doesn't matter about the x. The coefficients can be anything. It's what you focus on are the y's and the derivatives of y's. Only one can show up in any term, and it can only be to the first power. Okay? So that would also be linear. Not linear in x by any means, but we aren't even caring about that. in y. Okay. Now, here's a few counterexamples. 1 minus y prime, plus 2y equals e to the x. A pretty simple looking derivative written in prime notation rather than Leibniz notation. Can you see? Is it that one? Yeah. Okay. Linear or nonlinear? Make a guess. Nonlinear. Now the first term, no sweat there. You can distribute that y across here. You have a y. That's fine. But when you distribute this y here, you have a y prime times y, isn't it? Yeah, a y times y prime. That's where you lose your linearity because you have two y's in the same term. One is a function y and one's the derivative of that function y. You cannot multiply. That is not linear. This, no problem there either. E to the x, no problem there. It's the fact that you have a y times a y prime here. Can't have it. Okay? Okay, let's do it here. All right. d2y dx squared plus sine y equals 0. What you think? Nonlinear. What makes it nonlinear? That's sine. The sine's operating on a y. That makes y no longer linear. Now y is sinusoidal. It's not linear. Perfect. Okay. Does everybody see that? How about this one? d4y over dx4. Okay. Plus y squared equals 0. Pretty simple seeming function. Linear or nonlinear? Why? Yeah, this fourth here doesn't matter. That's linear, but this y squared is not. That is not linear in y. Perfect, perfect, perfect. Okay. All right. Now, back on page 2 that we did last time. And by the way, well, I have my clock in front of me, but sometimes I'll forget to look at it. So don't let me run over. This class goes till what, 10:45, right? So we got more than an hour, but don't let me go. Now, um, especially early in the morning classes, I may have to take a bladder break, okay? Because these things go 2 hours and 15 minutes, and in the morning I usually rehydrate. So at some point I might need to say, hey, let's take a quick one, okay? Y'all can go anytime you want to. I just can't get away with it, okay? So if we come to that, I'll just put a pause on the Screencast-O-Matic, and I'll probably pause the Zoom as well. I don't know. It doesn't really matter on Zoom. Do you think? You who've used Zoom before? Doesn't matter. We'll leave that running probably. That way you'll see when people start coming back. But just wanted to say that. But earlier back on page 2 in the text, which you probably don't have in the e-text, we talked about one of the goals in this course is to solve or find the solutions of differential equations. And I wish they'd get to them much faster than what this book does. This book spends this whole first chapter on introducing you to differential equations. They'll give you solutions, but they won't tell you how to solve them. We have to wait till chapter 2 before we ever solve the differential equations. But again, this section here is definitions and terminology. What do we mean by solving or finding the solution of a differential equation? And the definition is here in your text. And I know Ricky at least doesn't have a text. So let me hold it up because I don't think you'll be better reading this than trying to read my writing. Okay. But when I hold it up here, I can't read it. So there's the definition. Okay. Have I got it sort of centered in the camera? Where do I need to go? Up, down, right, left. That way? My right. Okay, your left. Okay. How's that? Okay. Now I'm trying to hold this steady. Can you see the whole definition? Okay, yeah, but I'm talking mostly to Ricky here. Okay. Readable? Okay. All right. All right, to bring it down. Okay, my arm's getting tired, so I'm going to bring it down. Okay, let me go over that definition with you. Any function phi, and they just love to come up with all different kinds of ways to express a function. Sometimes they express it just as y, sometimes they express it as z, sometimes as phi, sometimes as any Greek letter. They just love throwing in different things. So any function phi defined on some interval I, okay, and we'll talk about what that means, possessing at least n derivatives that are continuous on I, on that interval I, which, when substituted into the nth order ordinary differential equation, if it reduces the equation to an identity, meaning it's always true, that's said to be a solution of the equation on the interval. A lot of blah, blah, blah there, right? Okay. So what it means, you have to have a function, okay? It has to be defined on some interval. Now, right now, remember, we're talking about ordinary differential equations. What makes an equation or a differential equation ordinary? One and only one independent variable. If you had two or more independent variables, you're at best dealing with partial derivatives. That's not what we're talking about. One differential equation, okay? So this interval I is some interval of x. Think of the x axis, the x number line, some interval on that number line from 0 to 17, from -3 to +3, positive infinity to negative infinity. It doesn't matter. Some interval on that x-axis. That's an interval of x, okay? Possessing at least n derivatives that are continuous. So your phi function has to have n derivatives and they have to be continuous, okay? No derivatives that are discontinuous at some point in that interval. Like if something's derivative is minus x coming from the left, but positive x coming from the right, you can't include zero on that interval. It would have to be only on the left or only on the right, one or the other. It has to have at least n derivatives that are continuous on that interval, which, when you substitute back into the nth order differential equation, when you take those nth derivatives, you substitute them back in, you produce an identity. Then you say that phi was a solution to that differential equation. Okay. Again, a lot of blah, blah, blah. Now, in other words, if you think back of that form they were talking about before they introduced the normal form, your F, capital F, do you see that one? Okay. All right. That capital F, which is some function of x, phi of x, that was your y, phi prime of x, that was your y prime, phi double prime, phi triple prime, all the way up to the nth derivative of phi, has to have all of those. If that's equal to 0, if you can find, that's your differential equation, okay? If that phi works and makes that equation equal to 0 for all x's in the interval, I, whatever interval you've chosen there or wound up with, we say that then that phi satisfies the differential equation on that interval I. For our purposes, We'll also assume that the solution phi is a real valued function. We're not going to have it include complex numbers with imaginary components, only real valued functions. That it's only a real valued function. Okay. In the introductory discussion, we saw that, and this is one that we did last time, and rather than try to find it, no, here it is, right here. They just showed us a differential equation, rather bizarre one, and then showed us a solution for it. Y is equal to that. That now is our phi of x. We took the first derivative of that, plugged it in here, and found out, sure enough, that satisfied the equation. We said that then that phi of x, that y is equal to e to the 0.1 x squared, is a solution for dy dx equal to 0.2 xy. Okay, and that's good on every value. The interval here is minus infinity to positive infinity. Okay. Now, then they say sometimes it's convenient to denote the solution as y of x. Yeah, phi of x, y of x, it doesn't matter what you call it. Now, notice here we always talked about an interval. You cannot think of a solution of an ordinary differential equation without simultaneously thinking of the interval over which it's defined. So those are always going to go together. And like I said, that last one, the e to the 0.1 x squared, this interval was all real numbers. Perfectly fine everywhere. Okay? Not, that won't always be the case. If you have one with a tangent in it, you know it's not going to be defined at all real numbers because a tangent is only defined from something like a minus pi halves to pi halves because those are vertical asymptotes at those places. So that would be the maximum interval that you could talk about a function if there was a tangent x involved with it somewhere. Okay. Maximum size interval, I'll put it that way. The interval in that definition is called sometimes the interval of definition, the interval of existence, the interval of validity, the domain of the solution. You can call it all sorts of different names. That's what they mean. Okay. It can be an open interval, which either A or B, or both A and B are excluded. It could be a closed interval over which they're both included, or an infinite interval that may have an open or closed on one end, but go to infinity on the other end. Any of those are possibilities. All right. Now we're going to start doing what a lot of the rest of this chapter is going to be doing. And that is verifying a solution. That's what most of this chapter is going to be doing, verifying solutions of a differential equation. I wish they'd just go on and show you how to solve them, but all they're going to do now is give them to you and say, here, see if this is a solution or not. So this is beginning on example 5. If you got page numeration, it's the top of page 7 in the section. Okay? Here's the differential equation. dy dx is equal to x times y to the 1/2 power. Okay. Before we do anything else with that, let's classify that differential equation. What's its type? Ordinary. What's its order? First order. Is it linear or nonlinear? Nonlinear. That y to the 1/2 gives it away. That is a nonlinear, ordinary first order differential equation. Okay. Now, here's what they tell us. They suggest that y is equal to 1/16 x squared may be a solution for that differential equation. How will we verify that? What's the Jesus answer? Take a derivative. For those who weren't here last time, I hope I'm not being sacrilegious or anything, but I just, it's the way I think of it. A lot of churches where I've attended and stuff, they'll, back when you could go, they would have sometime in the service before they really start the serious preaching, they'd have children's church. They'd have all the kids come forward and they sit up front, and then some honcho would get in front of them and they would be waving at the parents or not paying any attention or scared to death because they're there in front of everybody. And usually they try to ease them into the situation by asking them some simple question. Now, of course, no question is simple to a kid up in front of a whole congregation of adults. And so they sit there like deer in the headlights. And then finally, some little kid, usually a boy in the back, will say, Jesus, because he figures that what answer could get you free in any class. You can't say there's anything wrong with answering that way. So I call that the Jesus answer in this course. Quite often, it will be take a derivative, okay? That usually works, okay? So let's take a derivative of y. If y is equal to 1/16 x squared, what is y prime? Or dy dx, is how they listed above. We'll write it in notation. What would that be? Say again? Okay, wait. No. All we're doing is taking a derivative of this equation here, okay? Y is equal to 1/16 x squared. Think back. Don't worry about what the answer is up here. Tell me what the derivative of that is. Just looking at that. You're back in Cal 1. Power rule. What would it be? Okay. You faded out on me there. It, okay, isn't it 1/8? 1/8 x. You're taking derivative. You're integrating, I think. Okay. Take a derivative. Exponent times coefficient, that would be 1/8, and then drop the exponent by 1. 1/8. Okay, maybe I copied it wrong. I can't even find my problem now. Yeah, my glasses aren't good. You're right. I copied it wrong. Okay, now I can see what's happening. X to the fourth. Okay, so that would be, you are absolutely right all the way along there. 1/4 x cubed. Perfect. Is that what you got? Yeah, sorry about that. Okay, so that's our derivative, we say. Okay, now we've done this part of the problem. We found what dy dx is. We know x is just an x, but y to the 1/2, we've got to also figure out what y to the 1/2 is from there. So if y is equal to 1/16 x to the fourth, what is y to the 1/2 power? In other words, the square root of y. What would that be? Anybody? Square root of 1 is 1. Square root of 16 is 4. So that's 1/4. Square root of x to the fourth would be, say again? No, x squared. Yeah, x squared. Okay, got it? So there's what y to the 1/2. If that's your y, and you need a y to the 1/2, that's what y to the 1/2 is. Okay, now let's take this, dy dx, and that, y to the 1/2, plug them in here and see if we get an identity. Instead of dy dx, we have 1/4 x cubed, and the question is that equal to x times 1/4 x squared, right? Where is it? There it is. Okay. This, the dy dx was 1/4 x cubed from what we did down here, okay, is that equal to x times y to the 1/2, which we did here, and we wrote that in there. And that's pretty obviously yes. 1/4 x cubed is 1/4 x squared times x, that'd be 1/4 x cubed. Sure enough, this is a solution for this differential equation. This equation here is a solution for that differential. This function here, this value for y is a solution there, okay? Now, let's think about it. For what is your interval over which that is a solution? What values of x will make that true? Frankly, I can think of none that would not make it true. Sure enough, y's can only be positive. But when you raise any x to the 4th power, that's going to be positive. So, no limit. Your interval of definition here would be minus infinity to infinity. Okay? Unless there's something else about the problem that would eliminate that, that's what we would have. Okay? All right. Let's do the B part. A little bit longer looking problem. Y double prime minus 2y prime plus y is equal to 0. And their suggestion is that y is equal to x e to the x may be a solution for that differential equation. Here's a differential equation. What is the type of differential equation this is? Ordinary. How do you know that's not a partial derivative? Subscripts, you're absolutely right. This would have been a y subscript x, your subscript x, subscript y. Yeah, you couldn't write it in prime notation. That has to be ordinary, okay? Is it what degree? I mean, what order? Second order, and is it linear or not? It is linear. Perfect. Your solution set, yeah, that's not linear because that's all dealing with x. Don't worry about that. Okay. Uh, so, what do you think we've got to do first? Take a derivative. And what rule are we going to have to use for that derivative? Product rule. How does that go? Okay, a little bit louder. Okay. Are you saying first times root of the second? A product of two functions. First times root of the second. X times e to the x. You're breaking up, so I can't hear what you're saying. Plus the second times the root of the first. And what is the root of the first? Derivative of x is 1, so that would just be plus e. Is everybody in agreement that is your first derivative of this function? Yay or nay? Yes, okay. But we don't have just the first derivative. We need that first derivative. We also need to take a second derivative, okay? So your y double prime would be what then? Well, that first term is exactly what the whole term was earlier. So that second derivative is going to be exactly what this one was. That's going to be the first term, product rule, be x e to the x plus e to the x. And then we've got to take the derivative of the second term. And what's the derivative of e to the x? E to the x. So that makes two of them. So that's just going to be x e to the x plus 2 e to the x. Yay or nay? All right, good deal. Now let's plug that back into our original equation. Okay, your y double prime, instead of that, we're going to write, I'm going to put them in parentheses so you can maybe see it a little more easily. X e to the x plus 2e to the x, that's your y double prime, minus 2 times, and your y prime was x e to the x plus e to the x, plus y, the y was x e to the x, and supposedly that's equal to 0. Now, if we can show that that is indeed equal to 0, we've said, yep, that's the solution. So let's take it and see. Let's clear the parentheses. First one's easy, you just erase them, but basically x e to the x plus 2e to the x minus 2x e to the x minus 2e to the x plus x e to the x equals 0. We just distributed basically the minus 2 across its, and that's what you got. And then when you take a look at that one, we see that you have an e to the x on the very right-hand end, another e to the x on the left-hand end, I mean x e to the x, but right in the middle you have a minus 2 x e to the x. So you got 2 plus e's plus x's e to the x, and 1 minus 2 x e to the x. Those add to 0. And then in between those, you have a 2e to the x and a minus 2e to the x. Sure enough, everything on the left-hand side becomes adds to 0. So you get 0 equals 0. That's an identity, if I've ever seen one. And that means that was a solution. Now, let's think. Are there any limitations on your x's here? Okay, any reason it can't be a negative number? Is what? Let's think about that. Okay. Now, if x were, let's take positive to begin with. We're pretty obvious that works, right? So let's think about what if x were negative. It was actually a negative value. Well, e to the x is never, ever, ever negative. It's always positive. Okay. So e to x is not going to influence the sign at all. So if x were a negative number, you would have a negative number, and the 2e to the x is a minus 2e to the x. That's going to go away. And then that would be a minus 2 times a negative number. That would make it a positive, but twice as big, right? And then you have another negative x. So that would be two negatives, single negatives, and one double negative, one 2 times a negative, a positive 2 times that. No, that would still work out right. It doesn't matter here at all. The places that you worry about negatives, basically, if they're under square roots, okay? Or following a logarithm. Can't have a negative in a even order of a root, and you can't have a negative in the argument of a log, okay? But usually in polynomial functions, the minus, if it happens in one place, and if it works going one way positive, when you negate it, it'll still work that same way, but because you're negating everything. The plus becomes a negative, the negative becomes a plus, and they still add to 0. So no, this I think is still going to be on the interval negative infinity. I haven't gone through and gory to tell the but I believe that would indeed be true. Okay. And it says here underneath this, note too that each differential equation possesses the constant solution. Okay. Okay. This isn't anything I was going to say, but here is another one. Y is equal to 0 here. is a solution because the derivative of 0 is 0 and the square root of 0 is 0. So 0 equals 0. That will work. Well, guess what? If you had y is equal to x to the fourth, when x is 0, y is 0. So that's not anything special, okay? Now down here, if y is equal to 0 will certainly also work because the second derivative of 0 is 0, first derivative of 0 is 0, and 0 is equal to 0. So that would certainly work. But when x equals 0, y is equal to 0 here. So y is equal to 0 is a solution in both. And why they say that, it's certainly true. It is a solution. And then it's also defined for all real values from negative infinity. Now, it's a solution of a differential equation that is identically zero on the interval I is said to be a trivial solution. Okay? Now, in both of these problems, the trivial solution was part of your general solution. But sometimes the trivial solution will not be a part of that general solution like we found here, and you have to look at that specially. We're not at the point of doing that yet, but just saying that. Okay. And now neither one of these are solutions for what we just did, I don't think. Okay. You can also talk about a solution curve. The graph of a solution phi of an ordinary differential equation is called a solution curve. Since phi is a differentiable function, it is continuous on its interval of definition. However, there may be a difference between the graph of the function phi and the solution phi. Okay? Put another way, the domain of the function phi need not be the same as the interval of definition or the domain of the solution. This is a lot of weasel words here, and we're going to talk about that in example 6. But here's sort of what they're talking about. You see this graph here? Obviously not defined x equals 0. Can you see that? Am I too far from the camera? Okay. Obviously not defined at y equals or x equals 0 or y is equal to 0. Okay. Not defined at x equals 0. Now, if that was your function, and by the way, that looks like p is equal to 1 over x. That looks like that thing. P is equal to 1 over x. This could be a solution curve. That would be the curve for that equation. However, that can't be a solution phi. One of these or the other of these. Either one of those could be a solution, but they both can't be a solution simultaneously. Okay? Because the interval has to contain everything. So your interval here would be all positive values of x, not counting zeros, or all negative values of x, not counting zero. So this one would be from negative infinity to 0. This one would be from 0 to negative positive infinity. And the zeros there are both either preceded or followed by parentheses, because 0 would not be included. So this would be perhaps a potential solution curve for a differential equation. But both sides of this could not be one or the other. You have to have an interval of definition, and it has to be continuous for it to work. Okay. Now, and like I just said, that was the function y is equal to 1 over x. Okay? It's considered simply as a function set of all real numbers x is the main set of all real numbers x, except x can't be 0, obviously, because it's in the denominator. Okay? So that earlier graph was the graph of that. The function y is equal to x. Okay. If you had a solution that said y is equal to 1 over x, that solution can only be defined on one interval. So if that was defined for positive values of x, the solution would only be from 0 to positive infinity, because the solution of a differential equation cannot include a vertical asymptote, basically. Okay, so it's wherever it's defined, in the problem. Okay, so the top of these represented the graph of the function y is equal to 1 over x. Okay, the bottom of these showed a possible solution graph. It could be either this one or it could have been that one, but it can't be both, because your interval of definition cannot include a discontinuity like that. So your solution would have to be defined on just one side or the other, but it cannot include a gap. Okay. Now, I don't know if you remember back when we were doing derivatives, some really complicated looking functions, you had to do implicit differentiation. You remember that? That was probably Cal 1. I cut out? Okay, sorry about that. Sometimes our internet is not real strong, and we are in a rain right now. I don't know if y'all are. Sometimes that does mess with we're on Spectrum, and we're down in a hole. We're right at the base of Red Mountain, and coming down to our house from 3 sides, you're coming downhill from all 3 ways, and going to the north, it slopes off gradually to the north, so it's going downhill from here to the north. So we're down in a hole basically, and we don't get a great signal, especially when it rains or is windy or something like that. So sorry about that, but let me know when I break up. But if you recall back in Cal 1, simple functions like we just did, what was that I wrote down wrong? Y is equal to 1/16 x to the 4th. Remember we did that one? I put an x squared there. Okay. That was a simple thing. You just take a derivative, you get the derivative. But if you had a really complex original situation, like xy cubed is equal to x or 7xy to the 1/2, that's not going to be an easy thing to do. The only way you could take a derivative of that is implicitly. You take, product rule, and where you have a y there, you have a dy dx that you put in there, and then you solve for the dy dx. Well, similarly, in differential equations, you have explicit and implicit solutions. And, frankly, this seems like a good time for a bladder break. Are y'all okay with that? Okay, I'm going to put this on pause for just a moment. All right, is everybody back? I see Cole's microphone's on. I see Melissa's on. Okay, and Ricky's is on. Dawson's still here. Yeah, okay. All right, so if everybody's back, we'll go on and get started again. Y'all might never have left, but I had to. Sorry. All right. And again, this isn't anything I want to write down, since all but one of you have ebooks. Let me, and she'll be getting one soon. Let me go on and just show you this definition. Give you a little background first. Again, like I said, when you have especially multiples where x's and y's are multiplied together, raised to various powers or whatever, in order to take a derivative of a function that looks like that, you had to do an implicit differentiation. Okay, that was back in calculus, probably Cal 1. A solution in which the dependent variable is expressed solely in terms of the independent variable and the constants, they can be in there. That's said to be an explicit solution. Just like every one I think we've done so far. Y is equal to 1/16 x squared. That was one for example 5. That was an explicit solution. Y is a function of x and x alone. Y is equal to x times e to the x. Y is a function of x and x alone. Okay? Y is equal to 1 over x, function of x and x alone. Those are all implicit solutions. Okay? Sometimes, however, you wind up with solutions that the dependent variable shows up in your solution as well, and you can't extract it. Okay? That's called an implicit solution. Okay? And then your trivial solution is always explicit too. Y is equal to 0. Often we'll be content to express a relationship as g of xy is equal to 0. Now this is a solution now that defines the function phi explicitly. So we're talking now a capital G. Remember, a capital F was your differential equation. Capital F is a function of x, y, y prime, y double prime, and so on. Your G is just going to be a function of x and y. You don't have derivatives in your solution, just that. But you can have y's in there. That's said to be an implicit solution of ordinary differential equation on an interval I, provided there exists at least one function phi that satisfies the relation as well as the differential equation. So it has to satisfy the relation between x and y that G expressed and the other. Don't get too bent out of shape over this. Let me show you that definition. I've basically just read it to you, but just if you want to get it down, is that anywhere close? Up, down, right, left, forward, back. Second, pull it away and to the right. What's that? Is that better? Oh, wait, oh, wait. My left or your left? Okay. 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 This way. Okay. Okay. It's a lot of weasel words. Just so you can see it, sort of absorb it. Don't sweat it. They'll be fairly obvious when you get them. Okay. Nothing too dramatic here. Just that's it. Okay. So let's do a verification. That's all we're doing right now, verifying of an implicit solution. Now this is a pretty simple one. Okay. Here's the equation. This time they give you the equation first and then give you the differential equation. They say this relation is an implicit solution of the differential equation. Here's the equation. X squared plus y squared is equal to 25. Now, before we go any further, what in the world is that? X squared plus y squared is equal to 25. Anyone want to hazard a guess? They do call it a relation, and indeed it is a relation. It's not a function. We'll talk about that in a minute. What's that an equation of? Say it a little louder. One more time. Okay, that's certainly true. Good observation. What does that graph as? Anyone have a clue? A circle of radius 5. Perfect. That is a circle of radius 5. And that's why it's not a function, because a circle, by definition, violates the vertical line test at least in 2 points, just about anywhere inside that circle, right? So that is a relation, and that forms a circle. Okay. Now here's what they claim. That is an implicit solution because you see your x's and y's are tied up there and can't really be separated easily. Of this differential equation, dy dx is equal to minus x over y. Okay. This is the differential equation that this is a solution to, or at least they claim. Okay. Now, we need to verify that. Okay. So what we have to do is take derivatives of the equation on top, x squared plus y squared equal 25, but do it implicitly. So what's the derivative of x squared? 2x. Okay. And what's the derivative of 2? I'm sorry, of y squared. 2y, but because y is the supposedly the dependent variable, you then have to do y prime. Remember? Or dy, let's call it dy dx, so that's what the problem calls it. 2y dy dx. Remember that? That's implicit differentiation. And what's the derivative of 25? 0. Okay? All right, so that's what I got. Did y'all follow that? Take the derivative of this, 2x, of x squared is 2x. Derivative of y squared is 2y times dy dx, because y is a function of x, is what we're understanding, and derivative of this is 0, right? Now let's, like we did before, solve for your maximum derivative. General form, remember that? Okay, so we'll subtract 2x from both sides and then divide by 2y. So we'll first subtract 2x from both sides. Okay, and that gives us a 2y dy dx is equal to minus 2x, and then divide both sides of the equation by 2y, and the 2's go out, and you have dy dx is equal to, I can't find it. Yeah, there it is. Dy dx is equal to minus x over y. And sure enough, there's your equal. Where is that? Oh, there it is. Dy dx is equal to x over y. Okay. Now, what's your interval of solution here? That's not good for all values of x. What values would that be good for? Okay. It's not totally obvious until you think about the graph of that circle. Minus 5 to positive 5. Okay. That's only good from minus 5 to positive 5. And they don't allow the endpoints from minus 5 to positive 5. In this notation, okay? They call that interval notation because I was running out of room. Minus 5 is less than x, and x is less than positive 5. They don't include the endpoint. And here's why, okay? And this actually gives you two possible solutions. Everything will depend on what y you're talking about, because y is also limited to minus 5 to plus 5. But it depends on which y you're talking about. Because if you think about this as a circle, draw a circle down here, because it's not a function, you can only have the top half of the circle or the bottom half of the circle. You can't have both. So it's either minus x over y, wherever that, oh, that's your derivative, okay? this will either work, because if you tried to solve this for y, you wind up with plus or minus. If you solve this for y, subtract x squared from both sides, be y squared is equal to 25 minus x squared. Then you take take the square root of y squared, and you get plus or minus the square root of 25 minus x squared. If you take the plus side, you talk about the top half of the circle, the bottom would be the bottom. Why can't you include the endpoints? Because dy dx needs to be defined. And since y would be equal to 0 at plus 5 or minus 5, you can't ever divide by 0. So that's why you have to exclude the plus 5 and minus 5. And then the nature of the problem means you have to stay between plus or minus 5. Okay? So that's why you have two possible situations here. It all depends on where your y is. Y has to be between 0 and minus 5 and 0, not counting the minus 5, but not counting 0, or 0 to plus 5, again, not counting 0, but going up to plus 5, because you can never divide by 0. Okay, so that one has two possible. The intervals are going to be the same either way, but those are your two possibilities there. The function itself is a circle of radius 5. You see that? Is that centered? Am I right? Okay. So you see the whole function, x squared plus y squared equals 0. That's that whole circle. But your solution, depending on where the y is either going to be the top half of that circle or the bottom half of the circle, but in neither instance can the endpoints be included. That's why they have the open circles there for the endpoints, because y can't be 0 by that solution, by that differential equation. Dy dx is equal to minus x over y, can never divide by 0. So y cannot be 0. Does that make sense? And that would be an example of an implicit differential equation. Now, you could have made it explicit by, as I said to begin with, redefining that solution to be y is equal to plus or minus the square root of 25 minus x squared, and then doing either the plus or the minus. And that could have been solved implicitly as well. You would have come up with the same solution. Now, while we're talking about solutions, we need to mention that quite often you have families of solutions. Differential equations, okay. Here's the best analogy that I have for this. A differential equation basically is a derivative equation. Remember, that's what I called it before, but they call them differential equations. Well, how do you undo a derivative? You integrate, right? And if you had an indefinite integral, you could have a whole infinite number of solutions. Because if you had an indefinite integral without limits on that, you always had to put a plus c, remember? When you did integration? Okay, so you could have a parabola that was up here, same parabola down here or down here, depending on what the plus c was. You have a whole family of parabolas that could be a solution when you integrated that, unless you knew one value. If you knew one value, you could home in and say, that's the one it's got to be. Not this one up here, not this one down here, but one somewhere in between, okay? And that's what a definite integral did for you then. It said, these two values, these are what you're doing, then you have one and only one solution, okay? But most of the time, okay? Well, the same thing is true of differential equations, okay? Now, if you have a first order differential equation. Your capital F differential equation is a function of x, y, and y prime, and that's equal to 0. Remember when we were doing that? I'll show you what we're talking about here. That's this right here. Okay, capital F equal is a function of x, y, and y prime only. Okay, and that's equal to 0. Well, that's going to be a one-parameter family of solutions because you only have one derivative there. Basically, think of that as your plus c. Now, it's not always going to be elevating it or detracting it. It just is changing it in some way. Okay, and this graph here shows a variety of solutions for some differential equation that uh, is equal to with different c values. And you see how the graphs can be one going up, one going down, whatever, but they all look somewhat similar, but that's a family of solutions. Okay. Now, and this particular one, they don't really specify it here, but this one, obviously y is equal to 0 is always a solution, isn't it? No matter which color or curve you have, they all go through 0, 0. So y is equal to 0 is the trivial solution is always a solution to that particular family of equations. They don't mention that here, but I just wanted to point it out to you because all of them go through that same point. Okay. Now, if you have a higher order differential equation, that f of x is f, capital F, is a function of x, y, y prime, y double prime, y triple prime, all the way up to the nth derivative of y, then your solution has to be a nth n parameters. It's an n parameter solution. So you're going to have all kinds of different solutions there, depending on all the different parameters n that you could have there. So a one parameter system is only going to differ a little bit in shape and direction or something like that. They're going to be pretty obvious. When you get two or more parameters, they can go all over the place. Okay. So we'll look at one. Now, if, however, you have a solution that doesn't depend on a parameter, and like I said in that first one, y is equal to 0 is a particular solution of that. The trivial solution is always true. It doesn't depend on any other parameter. It's just always going to be there. Okay, that is a particular solution. Has no dependence on, has no parameters that it depends on. Okay. The parameters of a family of solutions such as the capital G, remember how we said that? G is a function of x and y alone. We don't put any derivatives in your solution, but you can put your parameters in there. If it's a single parameter, you would have a C1. If it's a 7-parameter system, you'd have G as a function of x, y, C1, C2, C3, C4, C5, C6, C7. Okay? So however many parameters you have, those would also be part of your solution. And the parameters are arbitrary up to a point, meaning once you fix one, the others are pretty much fixed. Okay, or at least some of them are fixed. Okay. Um, so if you had a relation, this is very similar to the problem we just did, where you, or a short while ago, we did x squared plus y squared is equal to some number c. That's a single parameter equation, right? Depending on what c is, now obviously c cannot ever be negative. Not for this problem, right? Because x squared is always positive, y squared is always positive, or at least not negative, and the sum of those can't be negative. Could be zero. So what's that family of solutions? Those would be concentric circles about the origin. When c is equal to 0, you have the trivial solution. 0 plus 0 is equal to 0. Okay, that's your trivial solution. But then the others, say if c was equal to 1, then this would be a circle of radius 1. c is equal to 4, that's a circle of radius 2. c is equal to 9, circle of radius 9. So it would be concentric circles. I just picked the ones that were perfect squares, but you could have a 7 there, and then that would be a circle of radius square root of 7, whatever that is, okay? So that would be your family of solutions, a series of concentric circles about the origin. Okay? That's just one example, okay? However, c is equal to negative 25 would have no solutions because we're only dealing with real numbers, okay? So you have to have things that make sense. So let's look at example 8, and we're going to look at some particular solutions. For all real numbers of C, the one parameter family, I'll write this down first, y is equal to cx minus x cosine x. Okay, that's an explicit solution for the linear first order differential equation x y prime minus y equal to x squared sine x. Okay. Now, first they gave us a solution, a one parameter solution, and then gave us a differential equation. They say this is a one parameter solution for this differential equation. And then not on the screen. Okay. That this is the solution for that differential equation. A single parameter system for that system of equation. Why single parameter? Because the maximum derivative is the first derivative. Okay, the only derivative is the first derivative. So it's going to be a one parameter system. Okay, now they also say here verify. Most of the time they're going to say that. So what we need to do is take the derivative of that y, and what would that be? The y is equal to cx minus x cosine x. So what's your y prime? Derivative of cx would be c, that's yes in Spanish, minus, and what's the derivative of x cosine x? Good old product rule. Help me out here. A little louder. Okay, derivative of cosine is negative sign, so that would make that first. I'm going to have to go to a pen because my pencil lead just broke. Okay, that's going to make that a plus, and because derivative of cosine is minus sign, so that would be a plus x sine x, and then you have the derivative of the first times the second, that would be a minus cosine x. Now, I didn't plan very well, so mine's going uphill here. Here is your equation. Take the derivative of that, you get c. Derivative of this will be first x times minus sign, so that changes that sign to a plus, x times sine x, and then the derivative of the first times the second minus cosine x. Okay. So let's plug that in here and see if indeed that gives us our solution. Okay. So x times your y prime, my pen's not writing now, okay? X times y prime, that would be a cx plus x squared sign X.